Hello, my dear students. Welcome. Chalo, today we are going to tackle a very important topic from our current electricity unit, and that is the temperature dependence of resistivity. Now, don't worry at all, okay? We'll break it down so simply, I promise. You'll understand it perfectly and be completely ready for your exams. So, let's start with a simple question. We've all seen those old-style yellow light bulbs, right? The incandescent ones. Have you ever stopped to wonder, why does that bulb have less resistance when it's cold, but as soon as it gets hot and starts glowing, its resistance just shoots up? It's a bit strange, isn't it? Come on, let's solve this mystery together.
Okay, so to understand this properly, we're going to use a very simple story. Just imagine two different kinds of dance floors. I'm telling you this one single analogy. It will make the whole concept for both metals and semiconductors bilkul crystal clear.
First, let's imagine a medal. A medal is like a super crowded dance floor, okay? The number of dancers, and these are our electrons, of course, is already fixed, and there are a lot of them. Now, what happens if you turn up the music's tempo, which is just like heating the metal? What do you think? Well, the dancers just start bumping into each other more and more. It becomes total chaos. And this chaos, it makes it much harder for anyone to move smoothly from one side of the floor to the other. So, the main point, the crucial point, is this. For metals, the number of free electrons is already huge, and it doesn't really change with temperature. So when you give it more heat, the only thing that happens is that the fixed lattice ions, the atoms, they start vibrating more and more violently. And this leads to more frequent collisions for our poor little electrons who are just trying to pass through. So more collisions means more obstruction, and what does more obstruction mean? Higher resistance. Simple, isn't it? But the party in a semiconductor is a totally different story. It's like a party that starts almost empty. There are very few dancers on the floor. Now, when you increase the tempo, the heat, it actually encourages more people to get up from their seats and join the dance. So what happens? The number of charge carriers, or dancers, it increases dramatically. Yes, of course, they also collide a bit more, but, and this is the key, the effect of having so many new carriers to share the work is much bigger. It's the dominant effect, and this makes it so much easier for current to flow, so the resistance goes down.
All right, so I think the story is clear in our minds now, right? But for the exam, we have to speak the official language of physics. We need the marks. So let's look at the formula right from your textbook. And please, don't worry, it just says the exact same thing we just learned with our dance floor story, but, in mathematical language.
Okay, here it is. It looks a bit scary, but it's not. It says that the resistivity at any temperature T, we call this rho T, is equal to the original resistivity, rho naught, that's rho naught, at some starting temperature, T0. And all of that is multiplied by this simple factor, 1 plus alpha times the change in temperature, which is T minus T0. Now, this little symbol here, alpha, this is the temperature coefficient of resistivity. And trust me, it's the real hero of our story today. Now, I know alpha sounds a bit abstract, so to make it real, let's just look at an example like copper. For copper, alpha is a positive number. It's about plus 0.004 per degree Celsius. So what does a positive alpha actually mean? It's simple. It means that as the temperature goes up, the resistance also goes up. See? It's exactly what our busy dance floor analogy told us about metals. But why does this formula actually work? I mean, what's the physics behind it? To truly understand that, we need to zoom in. We need to look deeper into the microscopic world of the material. And this is where we'll see a kind of battle, a competition between two key factors. The first is the number of charge carriers, which we call N. And the second is the average time between their collisions, which we call tau. That's the Greek letter tau. And look at this table. This illustrates the whole story beautifully in one single place. Look, beta, just focus here. In metals, what happens to the carrier density, N? It stays constant. It's already high. It doesn't change. But as the temperature rises, the collision time, tau, decreases sharply. There are more collisions, so less time between them. And since resistivity is inversely proportional to tau, what happens? The resistivity increases. Simple. But now look at semiconductors. The carrier density N, it increases like anything. It goes up dramatically. The collision time tau also decreases a little, yes, but the increase in N is the real superstar here. And since resistivity is also inversely proportional to N, this huge increase in N causes the overall effect, a big decrease in resistivity.
Chalo, let's do a very quick numerical just to see how simple this really is. Okay, imagine we have a copper wire. its resistance, is 0.17 ohms at 20 degrees Celsius. Now we heat this wire up to 100 degrees Celsius. So what's the change in temperature? 100 minus 20, that's 80 degrees. Now we just have to plug these values into our formula. The new resistance will be the old resistance, that's 0.17, multiplied by 1 plus alpha times 80. When you do this simple calculation, you'll find the new resistance is about 0.22 ohms. That's an increase of 32%. See? Easy.
Okay, now for a very, very important section. Pay close attention. Let's talk about some common wrong ideas, some myths that can be what I call silent killers in your exams. You know, these are those small, silly mistakes that can cost you very precious marks. Let's make absolutely sure you don't fall into any of these traps. All right, here's the first big one. A lot of students think this. They imagine that when you heat a metal, the heat makes the electrons tired and they move slower. This is a very common and a very wrong idea. Let's see exactly why it's wrong. So the correct picture is actually this. A higher temperature gives the electrons more thermal energy, so their random zigzag jiggling motion, it actually becomes faster. But, and this is the key, it also makes the lattice ions vibrate much, much more. This creates a huge traffic jam inside the wire. It's these increased collisions that reduce the net forward movement, the drift velocity, not the actual speed of the electrons. So please remember, it's the collisions that are the real villain of the story here. And here is another tricky one. We always say in class, resistivity is a material property, right? So many students think, okay, if it's a property, it must be a fixed, constant number for that material. But this is only half the truth. The full truth is, yes, resistivity is a property of the material, but that property itself is dependent on temperature. Think about it this way. Think about the viscosity of honey, or even water. Viscosity is a property of water, correct? But we all know that hot water flows much more easily. It's less viscous than cold water. It's the exact same idea here. Resistivity is a property of copper, but that property has a different value at 20 degrees than it does at 100 degrees.
Okay, we are almost at the end now. Let's just quickly summarize the most important points, the things you absolutely must write down on your formula sheet and remember for your exams. This is the core of this entire topic, packed into a few key lines.
So let's revise. Point 1. For metals, as temperature goes up, collisions go up, and so resistivity goes up. And this means alpha is positive. Point 2. For semiconductors, as temperature goes up, the number of charge carriers goes up, and so resistivity goes down. This means alpha is negative. And why does this happen? It's because of the battle between collision time, tau, and carrier density, n. In metals, the effect of tau dominates, but in semiconductors, the effect of n is the big winner. And finally, for all your calculations, that formula is your best.
And finally, to leave you with a question to think about, you know your computer and phone processors, right? They are made of silicon, and silicon is a semiconductor. So based on everything we've just learned today, what do you think happens to the performance of your computer chip when it gets hotter and hotter? Maybe when you are doing some heavy gaming. Think about it. We'll discuss it in the next class. Until then, keep learning.